equals, which they're not, of course, okay? We notice how this equation differs from the general one, okay? Don't have an explicit dependence upon y. So when I look at the differential equation, all I'll see is the independent variable x, its first derivative and its second derivative. Y itself will not appear in the equation, okay? Okay. Now, to solve this type of case one, what we do is we set dy dx equal to u of x, obviously, right? We're going to basically reduce the order of this thing, okay? And then in general, what's going to happen is you're going to get what's going to happen now becomes f of x, y prime, we just said is u, and y double prime will be du dx is equal to 0. So now we look at this equation, and it looks to me to be like a first order equation on u, right? Okay? Many times, not always, you can actually integrate this to get u as a function of x, okay? It doesn't work all the time, okay, but there are a lot of problems where it does. So imagine that we could integrate this and actually get u as a function of x. We'll pick up a constant of integration, of course, right? And then what do we do? Well, our substitution was dy dx equals u, so after solving for u as a function of x, plug it back into here, one more integration to get y, okay? That's the idea. So let's look at an example of that, okay? And I'll give you an example for each case, okay? Let's see the equation that I have. The equation I have is going to be y double prime is equal to 2x times dy dx squared. There's no way you can do that based upon what we've done so far, right? It's nonlinear. Sec with respect to x is equal to 2x times y prime squared. Okay. Well, we look at it, does it match case one? Yes. Y does not appear explicitly. I see an x explicit, I see a y prime and y double prime, but there's no y that appears in that equation explicitly. So let's make that substitution then, okay? So let u equal y prime, and y double prime is u prime, okay? Same as over there. What's on the left-hand side? Second y respect to x is just the u dx, okay? That equals 2x times y prime squared, which is u squared. Okay? So this is separable. You're lucky. Du over u squared equals 2x dx. Okay? We can integrate this, right? That's just minus 1 over u, right? Just the derivative of u to minus 1 is minus 1 u to minus 2. So I need that minus over there. That equals x squared plus an arbitrary constant c sub 1. Okay, that was easy enough. Let's get u over here then. What's u? Take the reciprocal and put a minus sign on it. It's minus 1 over x squared plus c1. Okay? And of course, that's just, remember, you can't stop over here because the original equation was y versus x. So you have to get y as a function of x. This is like an intermediate step. At least you have the slope now. We have dy dx, right? So now we have the equation dy dx equals minus 1 over x squared plus c sub 1. Okay, again, boy, that's separable, right? So we have dy equals minus the differential of x over x squared plus c1, right? And of course, y therefore is minus the integral of dx over x squared plus c1 plus an arbitrary constant c sub 2. I'm not going to take up your time to do the integration. You can look this up in a table or do it yourself. It comes out, you have to be careful. There are 3 cases, and I'll just do them. Case A is suppose c1 is equal to 0. Okay, that integral you can do, right? Just minus 1 over x. And if c1 is equal to 0, let's just do that one. I don't have it written down. Suppose c1 is equal to 0. Then y equals c sub 2 minus the integral of x to the minus 2 dx. Right? Okay? And that integral is x to the minus 1, right? Right? Okay? that's the solution when C1 is equal to 0, okay? And the other ones I'll just write down. What happens if C1 is greater than 0? In that case, you'll find out that the solution is y is equal to C sub 2 minus 1 over radical C1 times the arctangent of x over radical C1. Okay? And then finally, in case when C1 is less than 0, write it down here, y is equal to C sub 2 plus 1 over the square root of negative C1, where C1 is negative, right? So that's okay. And then you get an inverse hyperbolic tangent. You do this in terms of logarithms also. Well, this is just one way of doing it. X over radical negative C1. Okay, so except for this last part, it's you know, pretty straightforward, right? I wouldn't give you something like this on the exam with the arctangent or something like that, okay? The idea to illustrate, though, is that here's a rather, it's not complicated, but basically it's very nonlinear, right? Because it has the square of y primed in it, yet you are able to actually get an analytical solution for this. Okay, and the trick was to recognize that it falls under this first case where the dependent variable y does not appear explicitly. Okay, the second case is you can anticipate it's going to be when what? The independent variable is missing. And this happens in mechanics all the time. Matter of fact, I'm going to do several problems. One is going to be launching of a rocket out of the, Earth's gravitational field, and it comes under the class of this case 2 that we're going to do right now. Case 2 is independent variable missing from F. Independent variable absent, missing. Okay? What happens there? So we have the general form, but now it's f of y, y prime, y double prime is equal to 0. Notice that I dropped the x. So you look at your differential equation, you'll see the second y respect to x, you'll see the first derivative, you'll see y, but you won't see x. Okay? And what's the substitution over there? So in this case, we start the same. We said let dy dx equal u. Okay. That's the first step. Okay? Now, if we do the same thing as we did before, that is now let y double prime be du dx, we kind of destroy it because now we're introducing x. So the question is, can I express y double prime without getting x involved explicitly? And we can if you use the chain rule. The second derivative of y with respect to x, okay, well, du dx, but I don't want that, right? Because it brings x in there. Let's use the chain rule. That becomes the derivative of u with respect to y times derivative of y with respect to x. Or y double prime gets replaced now by what? What's dy dx? That's u. Okay? U du dy. Okay? Then the equation becomes of the form f of y, y prime, u, right? And then I got y double prime, which is u du dy, is equal to 0. And the idea is hopefully we can integrate this to get a relationship between u and y. And then once we know u is a function of y, to go back over here and try to get x and y relationship. Okay? Like I said, this one occurs quite frequently in mechanics problems. Okay, and let's do an example of that. Okay. Example number 2. Oh, this one is actually simpler. Okay, so example 2. The differential equation is y, second derivative of y with respect to x, equals dy dx on u squared. Okay, so we got on the left y double prime, y prime squared. Okay? I look at that equation and it definitely falls under case 2 because I don't see x in there explicitly, right? So we're going to make these substitutions, okay? I'm going to plug in for dy dx u, and for y double prime, I'm going to plug in u du dy. So the y stays, right? The y double prime is u du dy. And then on the right, I've got y prime squared, which is just going to be u squared. Okay. Now, it's tempting to divide through by u, but we know from, right, like week number 1, you have to see maybe that's a special case. So, before we divide through by u, we say, is u equal to 0 a solution? Okay, well, what is u? U is dy dx, okay? So, if u equals 0 is a solution, that means dy dx equals 0, which means y of x equals a constant, i.e., is y of x equal constant a solution of the original equation? And you can do that by inspection. It is, right? To set y equal to a constant, this kills it on the left, and the derivative gets killed on the right. So we do have that solution, put it to a side, y equals constant. But what we'll see is that we get the solution, u not equal to 0, it will subsume that case. Okay, we see that happens many times, so it's not a singular solution. Okay, so now, okay, we've taken care of the case u equal to 0. Now let's look at the case u not equal to 0. I divide through, I get y du dy is equal to u. Right? U equals u, so we get y times the differential of u is equal to u dy. Let's divide both sides by y times u. I get the differential of u divided by u equals dy over y. That's so easy. It's easy to integrate, right? Okay? So if we integrate that, this becomes a logarithm of u. Let's assume u is positive to make things simple. Okay? So usually in the problem at hand, you will know if it's positive or negative. Log u equals log of y plus an arbitrary constant. And just for simplicity, I'm going to write that as the log of c1 rather than c1. Okay? Bring the log to the other side. I've got the logarithm of u over y, right? Just log u minus log y equals the log of the constant c1. The only way two numbers can have the same logarithm if they're equal. So we find that u is equal to c1 times y. Okay, almost there. Now, of course, we have to introduce u as dy dx to see if we can integrate that. So here. Okay. But u is dy dx. So I get dy dx equals some arbitrary constant times y, right? Now it's separable again, right? So I got the differential of y divided by y equals c1 dx. Integrate both sides, we got the logarithm of y equals c1x plus an arbitrary constant is called c2. Now just from and this is where people in exams always screw this up. Again, y'all know your laws of logs, right? Y is then the exponential of c1x plus c2. That becomes e to the c2 times e to the c1x. Let's call e to the c2 c3. c3 e to the c1x. So the solution to our equation is y equals some arbitrary constant, doesn't matter if it's c3, c4, right? Exponential of another constant times x. That's the solution. And you can check. If you put y equals arbitrary constant e to a constant x into the equation, it will solve. And let's go back now to that singular solution that we had. Remember we said y of x equals constant is also a solution. Does my general solution contain that? Yes. If you plug c1 equal to 0, right, that exponential becomes 1 and you get y equals constant. So therefore I don't need that other one. This is the general solution to the equation. Any questions on that? Okay. So it's a matter, again, these are the only two cases we're going to do. Okay? Nonlinear second order, either the independent variable is missing or the dependent variable is missing. Now, there's something that the book does not do, which I thought is interesting, okay? Many times, there's sort of like two hurdles, no matter if it's case one and case two, right? The first hurdle is doing the integration, like over here, let's go to this one. You have to get u in terms of y. That's hurdle number one. Hurdle number two is what? Do the second integration where you plug in for u. I'm going to show you a problem now where you're going to get stuck on that, okay? But what happens is that fortunately, we can do it with method one or method two, and then we're going to get parametric equations. This is not covered in the book, but it's an interesting thing to know. Okay, and that'll be it for the number of some nice physical examples. Okay. Okay, solution in parametric form. This is the example. And again, this type of problem is not in the book. It's interesting to know. Suppose the equation is the following. I got dy dx, y prime squared, times the second derivative of y with respect to x equals 1 plus y prime squared. Okay? This equation actually occurs in hydrodynamics, okay, believe it or not. Okay, so you get y prime squared times y double prime, y prime squared, which is y prime, y double prime. So clearly what's causing the nonlinearity here is y prime squared. Now, in this case, I could try either technique, right? Because the independent variable x is missing and the dependent variable y is also missing, okay? So let's go and do it both ways. Okay, so first solution, note y is absent. Again, I mean by that, it's just not explicitly in there, okay? So we know what we're going to do there. We're going to set y prime equal to u, right? And y double prime is going to be just u dx, or u prime. Okay? Dependent variable is missing. Okay. So y prime squared, that gives me a u squared, right? Y double prime is the u dx. That equals 1 plus y prime squared, that's just 1 plus u squared. Okay. So I find that du dx is 1 plus u squared divided by u squared.